This is Professor Likely. In this particular semester, he has a lot of work to do. Thus, he is in constant search for the perfect team of teaching assistants to help him. There are 5 who he previously worked with. Although he enjoyed the work with them and they did their job in doing his paperwork quite well, 5 TAs were a little bit pricey and complicated to work with, so he wants to minimize his team. But the workload stayed the same, so he wants to hire in such a way where his team still performs well, but the organization is less complex and also cheaper. Therefore, he fires John, who he believes is his most useless TA. But did this pay off? Well, the topic of today's video might help: the likelihood ratio test. You're asking yourself what that is? No problem, the tutors do as well. So, let's answer the questions that you and the TAs might have. In particular, we are going to talk about the statistical problem the LRT is applicable to, state what it measures, how to use it, and when it might be not so handy. So, with all of that, let's start. We thought it might be a good idea to just refresh the definition of some keywords in order to understand the likelihood ratio tests a little bit better. First of all, we want to distinguish between a nesting model and a nested model. A nesting model is more complex, meaning that it has more parameters. A nested model, in contrast, means that it is nested under the nesting model. Therefore, it is a simpler model, which can be seen as being equivalent to less complex, so it has less parameters than its nesting model. Therefore, L is smaller than K. The complexity of the model leads us to the degree of freedom, illustrating the number of parameters -1. These definitions are already the most important tools to understand the likelihood ratio test. So, let's get started. Imagine the TA team from earlier. Each of them contributes to the work that is done and influence the quality of that work. But do we really need a team that is not only pricey but also complex to manage? Or can we spare one team member and still get similar and satisfying results? Well, just switch the team with the model, their paperwork with the data that needs to be approximated, and each TA with a parameter, and you get the building blocks for a likelihood ratio test. Here, the organization of that team corresponds to the model complexity, as it also increases with more TAs, and their payment to the computational work that needs to be done. Both of which we obviously want to minimize. But how? For that, let us spin our simile a little bit further. Let's assume the more complex 5-person team is a nesting model M, which approximates some data. Here, we already found a model with K, here 5, parameters which approximates our observed data X quite well. But again, we want an easier and cheaper model, one that is nested under the nesting model. So, that model is supposed to have a smaller degree of freedom than K, and therefore less parameters. You remember Professor Likely and think, okay, no problem, I will just fire someone, aka delete a parameter by setting it to 0, and thus the degree of freedom is lower, here 3, and the model is less complex. And you would be right. Well, sort of, because you always have to remember we are looking for a model to approximate the data. Making it less complex also means that our model could get worse. So what we have to think about is, can I reduce the degree of freedom in such a way that I do not significantly decrease the performance of the model? And at this point, our likelihood ratio test comes in. It allows us to estimate if a nested model is significantly worse in terms of performance than its nesting model. For that, let us look into the math that gets us to our likelihood ratio test. First of all, quick reminder, Theta is the tuple of all weights / parameters of M, and so is theta 0 for M0. The likelihood function of M is defined on the left, and for M0 on the right. In our case, the likelihood functions give access to estimate the performance of each model on the data. So the likelihood represents the goodness of the fit. To get the likelihood ratio, we have to divide the likelihood of the nested model by the likelihood of the nesting model. Taking the natural logarithm of this division, we get the differences between the Ln likelihood functions. By multiplying it with -2, we are realizing that this term is chi-squared distributed, with k minus L degrees of freedom. This resulting value is the likelihood ratio, LR for short. Due to this interesting property of the LR, we can perform a hypothesis test. Therefore, we are using a null and alternative hypothesis. The null hypothesis, H0, indicates that the simple model M0 is not statistically worse than M at fitting X. The alternative hypothesis, on the other hand, means that M0 is statistically worse than M. Figure 1 shows a graph where the nested model M0 is too different from the original nesting model M. This means that the parameter and weights that got cut off, parameter theta, were too important for the dataset, resulting in a large LR value. This means that we reject the hypothesis H0 and thus keep our original model and complex nested model M. Here we are accepting the H1 hypothesis. When you think back to our example, this would mean that our TA John was too important for the team and the workload just couldn't be done properly without him. In figure 2, we see the opposite. The less complex nesting model M0 is similar to the nested model M. The LR value is therefore small enough and we are accepting the hypothesis H0 and thus getting rid of our complex model M and keeping the simple M0 model instead. To better understand what happened in the two previous figures, we're going to go through it step by step now. First, we're drawing our two axes. Pay attention to our labels. Theta on the horizontal one, standing for the number of tuples of all weights and parameters. The vertical is labeled with the logarithmic likelihood independency of theta. Then, we're drawing our graph. Taking our variables from the original nesting model M, we are looking at the height of the graph at the position theta. After that, we are having a look at our simpler nested model M0 at theta 0. The corresponding value on the vertical axis is of interest here. Now we have the two logarithmic likelihood values. By calculation, with the difference, we're getting the value LR. The larger the value LR gets, the more the two likelihoods of the models are getting different, and therefore, the more likely we are to reject the hypothesis. The most important points to take with you from this video are that we are always starting with the dataset and the corresponding likelihood function, called a nesting model. This nesting model is quite complex, but fits the dataset well. Trying to simplify this function, we cross out some parameters by setting them to 0. Thus, we are creating a nested model. We have to check if the likelihood function of our nested model is as good as the likelihood function of the complex model by approximating the dataset. We can reformulate this problem to a hypothesis test. H0 states that M0 is not statistically worse fitting the data, whereas H0 states that M0 is indeed worse fitting the data. And here we will not explain the calculation of the likelihood ratio again. You can simply pause the video and jump back to the corresponding part. And with that, that's all you need to know about the likelihood ratio test. Oh, but one TA's question was still left unanswered. When is the likelihood ratio test not applicable? Well, you have to pay attention. The likelihood ratio test does not take complexity into consideration. Therefore, further tests would be recommended to get the perfect model. Here, one example would be AIC. So now that would be it. and everything you need to know about the likelihood ratio test. If you have any questions, don't hesitate to ask us. We would be glad to help you.